Let us begin today's class with a quick recap. Now you know that sound is produced by vibrating objects and need material medium for its propagation. When a wave passes through a medium, the medium does not move along the direction of the wave. Only the particles, the medium particles, vibrate about their mean position. And in doing so, the transference of mechanical energy takes place from one point to another. There are two basic types of wave motion for mechanical waves: longitudinal wave and transverse wave. We shall be doing both of them one by one. We will begin with longitudinal waves. A longitudinal wave is a wave in which the medium particles vibrate in the same direction in which the wave is moving. A longitudinal wave has been illustrated in a figure over here. In this figure, the direction of the wave is shown along PQ in the horizontal plane, and the direction of the vibrating particles is also along PQ parallel to the direction of the wave. That means the particles of the medium are vibrating back and forth in the horizontal direction. The same has been depicted in this particular animation. Kindly observe the motion of the red circled dot. You will notice that the distance between the particles in the longitudinal wave motion, at some places that distance is closer and at some places it is far away from each other. I hope you must have observed this particular thing. Longitudinal waves propagate in the form of compressions and rarefactions, and this is what was depicted in that animation. Before we discuss further, it is necessary to understand the words compression and rarefaction. Compression is a region of the medium in which the particles of the medium come closer. That is, the distance between the particles decreases temporarily than the normal distance. Due to the decrease in the distance between the particles, their volume as well as pressure decreases and the density increases. On the other hand, rarefaction is a region of the medium in which the particles of the medium get rarefied. That is, the distance between the particles increases temporarily than the normal distance, due to which the volume increases as well as the pressure and density decreases. This animation clearly shows that the particles do not move with the wave. They simply oscillate back and forth about their individual equilibrium position. This is the particle model of the longitudinal wave. Pick a single particle, let's say the red one, and watch its motion carefully. When the vibrating particles come closer to one another than they normally are, there is a momentary reduction in the volume and a compression is formed. I hope you have identified those regions. On the other hand, when the vibrating particles move farther away or farther apart from one another than they normally are, then there is a momentary increase in the volume and a rarefaction is formed. It is clearly depicted in this animation. Hence, this animation clearly demonstrates the difference between the oscillatory motion of the individual particles and the propagation of wave through the medium. When a wave passes through a medium, then some properties of the medium like density, volume or pressure changes. So waves are represented graphically by showing how some of these properties of the medium change when a longitudinal wave passes through it. Now in a longitudinal wave, the particles of the medium vibrate parallel to the direction of the wave. Hence, a longitudinal wave cannot be represented by a displacement distance graph, because finally the particles come back to their original position. A longitudinal wave over here is represented pictorially by showing the regions of compressions and rarefactions. C stands for compression and R stands for rarefaction. In a compression, the density of air is higher, while in the regions of rarefaction, the density of air is low. Thus, when a longitudinal wave passes through air, then density of the air changes continuously and so is the pressure. And this is depicted in the second one. The darker regions are the compression regions where the pressure is high, and the lighter regions are the rarefaction regions where the pressure is low. In this graph, where we have plotted pressure on y-axis and time on x-axis, this particular graph very well shows the observation that was made by you in some of the animations before this slide. The horizontal line represents the normal pressure of the air, that is the atmospheric pressure. And all the points above this line represent greater pressure, and below this line it represents low pressure than air or than the normal atmospheric pressure. So these peaks above the reference line are depicting the regions of compression, while the peaks at the bottom depict the regions of rarefaction. I hope you have understood this graphical representation of the longitudinal waves. This is the slide which very well explains you the differences between compressions and rarefaction. So on the basis of distance between the particles, compression is that part of the longitudinal wave in which the particles of the medium are closer to one another than in their normal state, while rarefaction region, in the rarefaction region, the particles of the medium are farther apart than in their normal state. On the basis of volume of the medium, there is momentary decrease in the volume, while in the rarefaction region, there is momentary increase in the volume because the separation of the particle increases. And because of decrease in the volume in the compression region, the density is higher of the density of the particles in that region is higher than the normal, and hence is the pressure, while in the rarefaction region, the density of the particles are lower than the normal, and hence the pressure is also below the average or the normal value of air, normal value of air pressure. We shall be doing now some examples of longitudinal wave. The first one is that of a spring. This particular figure demonstrates or shows the position of the spring in the normal condition. It is fixed at one end. When the spring is pushed or pulled, consecutive regions of compressions and rarefactions are formed. This animation shows this concept clearly. In a spring, the compression is that part in which the coils or the turns are closer together than normal, and rarefaction is that part in which coils or turns are farther apart than normal. Now, if the free end of the spring is moved to and fro continuously, then longitudinal waves consisting of alternate regions of compressions and rarefactions are formed. This is shown over here. Hence, when a wave travels along the spring, then each turn of the spring moves back and forth only by a small distance in the direction of the wave. Since the turns of the spring are moving back and forth in the direction of the wave, therefore the wave which travels across the spring is longitudinal in nature. Sound waves in air are also longitudinal waves. The animation shown here is that of a wave produced in air when a sitar wire or violin wire is plugged. Observe carefully the pattern of the wave so formed. The next example is that of a tuning fork, the vibrations produced by a tuning fork. A tuning fork serves as a useful illustration of how vibrating object can produce sound. The fork consists of a handle and two tines. When a tuning fork is hit with a rubber pad or a hammer, then the tines begin to vibrate. The back and forth vibration of the tines produce disturbances of surrounding air particles. As a tine stretches outwards from its usual position, it compresses the surrounding air molecules into small region of space. This creates a high pressure region next to the tine. As the tine then moves inwards from its usual position, the air surrounding the tine expands. This produces a low pressure region next to the tine. As the tine continues to vibrate, an alternating pattern of high and low pressure regions are created. The high pressure region are called compression and low pressure regions are called rarefaction. Next is transverse wave. Transverse wave is a wave in which the particles of the medium oscillate or vibrate perpendicular to the direction of propagation of the wave. Unlike in the case of longitudinal wave, where the particles used to vibrate along the direction of propagation of the wave. And this has been shown to you in this figure. The direction of wave is from M to N. That means in the horizontal direction. and the direction of vibration of the particle of the medium is along AB, that is perpendicular to the direction of the wave, and the particles of the medium vibrate up and down perpendicularly. There is a simulation over here, and with the help of this simulation, you will be able to understand better. Observe the motion of the particles, which is up and down, and the wave is traveling in the horizontal direction. That is how transverse wave propagates. The animation shown in the previous slide for transverse wave was the particle model. This animation illustrates the difference between the motion of the wave and motion of the particles in the medium through which the wave is traveling. Kindly note that the direction of the particle is up and down, that is vertical. Kindly observe the arrowhead, and the direction of motion of the wave is horizontal. Please observe carefully the arrowheads, and the blue arrows here, they show the direction of motion of the wave, while these arrowheads are the particles that are moving up and down in the vertical direction. In both the simulations, we have observed that when vibrating particles move upwards above the line of zero disturbance or the line of reference, they form an elevation or hump. And when the vibrating particles move downwards below the line of reference, they form depression. This has been shown over here. There are certain peaks above the line of reference and certain peaks below the line of reference. The peaks above the line of reference are termed as crest, and peaks below the line of reference are termed as troughs. The same peaks were termed as compression and rarefaction in case of longitudinal waves. So let's see what is the definition of crest and trough. Waves have moving crests or peaks and troughs. A crest is the highest point the medium rises to, and a trough is the lowest point the medium sinks to. Therefore, we can define crest as a point on the wave where displacement of the medium is at the maximum. That means here, and you can see clearly, or in this particular figure. The maximum displacement of the medium is upwards, and that is known as crest, and the point on the wave is the trough if the displacement of the medium at that point is minimum shown at the bottom peaks. These are some examples that are observed to have transverse waves. The first one is that the wave produced by moving one end of the rope up and down, whose other end is fixed. Kindly observe this simulation. This is how a transverse wave propagates when one end of the rope is fixed. The second example is that of water wave. Now you are very much familiar with this simulation. What you have to observe is the particles, how they move up and down when they form ripples. You can see a similar shape is formed at the surface of the water, while the particles nearly at the bottom are not moving. They are almost static, but the particles at the top are moving, and hence we say that transverse wave is formed on the surface of water, right? So this was the second example. Third example is that of vibrations of stretched strings. And finally, the light waves are also transverse in nature. If you remember in the previous video when we were discussing about the differences between light waves and sound waves, I clearly mentioned you one point that apart from the points that were mentioned in the differences, there is one more important point of difference between the two, and that is that sound waves are longitudinal in nature while light waves are transverse in nature. That means in the light waves also the particle's motion is perpendicular to the direction of the wave, and hence these are, that means the light waves are transverse in nature. So these are the four examples of transverse wave. However, there are some more which I am leaving for you to find out. By now, you must have understood the nature of both longitudinal and transverse waves. We will now summarize today's portion. With the help of these two simulations, you would be able to distinguish between longitudinal and transverse wave on the basis of motion of the particles more clearly, and this will be a revision for you also. Now imagine that the blue balls over here in this simulation as well as in the second simulation are the particles in a material. These particles are bonded to other particles in both of them, right? And therefore, the motion of one particle affects the motion of other particles around it. So let us see the first one, the transverse wave. You have seen clearly how the transverse wave propagates, right? Here you note that the particles are vibrating in a vertical direction while the wave itself is transferred horizontally. On the other hand, in the longitudinal wave, the particles are vibrating horizontally and the wave is also propagating in the horizontal direction. On gathering all the points together for longitudinal as well as transverse wave, we can finally distinguish between these two waves on the basis of these 4 points. First is the particle behavior or the motion of the particle. In longitudinal waves, the particles move or oscillate back and forth along the direction of propagation of the wave. While in a transverse wave, the particles oscillate perpendicular to the direction of propagation of the waves. Longitudinal waves consist of compressions and rarefaction, while transverse wave consists of crest and trough. One very important thing is that longitudinal waves can propagate through all the three medium, that means solid, liquids as well as gases, but transverse wave can only travel through solids and surface of water. This you must have seen in one of the simulation earlier. And the last one, longitudinal waves, whenever they travel, they cause change in the volume and density of the medium and as well as pressure. On the other hand, when transverse wave propagates in any medium, then there is no change in the volume, density or pressure observed.